Thanks for coming. I'm going to go ahead and get started. Presentation today is about big data, but mostly it's about security at scale, because big data really represents huge, massive, large, whatever you want to call it, scales of systems and data. And I want to start off with just a simple quiz here. How many people believe A is darker than B? Quick show of hands. How many believe B is lighter than A? No, the squares themselves. The shades of gray. Anybody think they're the same? Yeah, so a couple people have probably seen it before, right? Okay, so this is a quiz that shows that with a little bit of illusion, the human eye makes a mistake. Basically, our machine, if you will, is trained in such a way that we make a mistake in our calculations. And so the point of this presentation is really that as we get to larger and larger scale, I really want to make people think about how we need to change our definitions and change the way that we look at security. Mostly because we'll make errors that we're making today, and they'll be worse. Because we do make a lot of errors, it's obvious, right? The Heartbleed and so forth talks about bugs that we made, obvious bugs. Why didn't we catch this sooner? Why didn't we spend more money? A lot of our assumptions that we have about systems today break when we get into larger systems, and so we need to change the way we look at those systems. All right, I'll do some more quizzes in a little bit. But first, let me back up and say, who I am. My name's Davi Ottenheimer. I had a company called Flying Penguin, and now I'm part of EMC. You may have seen my latest breach report here on breach analysis. I found out that the impact underwater is actually much less than impact in the air. So here's an example of a whale that's breaching. This is an actual orca that's launching multi-ton. Anyway, so again, the point of the company Flying Penguin was to emphasize that penguins do fly actually underwater. And a lot of times, again, we don't think about things in a way that we're open to new ideas. We have a knowledge base built up. And so when you think of flying, you think of air. But actually flying is the mechanism that the animal uses. And so when penguins are underwater, it's a thicker medium, but they're still flying. And a lot of birds actually fly underwater. Actually, some do both. They swim and they fly underwater as well as above. So basically, where I came from, I really started out, my parents are anthropologists, so I spent a lot of time working with them. And I think it was 1985, I actually worked on a paper called Shintiri, the Secret Language. We found a language that was hidden in a culture in Africa. And so for a long time, I've been doing presentations and speaking. I then spent some time doing some bike and sailboat racing. I still race sailboats, which it turns out when you think about big data and analysis, it's very linked to competition. So if you look at professional athletes, as well as chess masters, they have an inbuilt system of finding flaws very quickly, because to win, they have to be able to reduce those flaws. So I'm finding more and more as I do my research, the areas of inquiry that are most interesting to me are areas where people are successful in competition. Watson is an example of this, where you try to build a machine that can beat a human. Why do they make mistakes? Where do they make mistakes? So how do you build systems that are resilient to failure? Anyway, so I also did a lot of research around ethics, humanitarian intervention, so I've been speaking lately on active defense and those sorts of things. Again, where are flaws, where are exposures going to hurt us most at a macro scale? My degree is in international history, so I do tend to talk too much about examples from the past, so you'll find some of that interspersed in here. And then this is my 20th year, so time flies, and since '94, I've been working in information security, which is kind of scary. And a lot of things haven't changed. I actually am working on a book called Securing Big Data. And one of the reasons it's delayed, it was supposed to come out early this year, is because things are changing so fast in the world of big data security. For example, I'm finding that some of the things I was writing about are being fixed, and so I can't say, you should fix this, because the release comes out just as I'm writing that chapter about the fixes I want to see. So I've shifted to analysis of what things are most important, what things you should get first, because the fixes that are coming out are actually pushed out. An example of this is patching. We're talking about right now in the Hadoop common distribution list about whether or not you should patch Java 6. So Java 6 support ended already. In the security community, this is like a no-brainer. Why are you even using Java 6? But today, even in the discussion list, Cloudera is saying, no, leave Java 6. It's perfectly good because of availability. If you get rid of it, it'll break everything. Classic developer argument, right? Availability is most important to us. Don't get rid of Java 6. Whereas a security person says, if you leave Java 6, there will be no availability. Do you want me to make somebody I was working with called this the elephant gun, but do you want me to make a tool that shows you why Java 6 is a bad dependency inside your environment? So these are the sorts of changes that are happening fast, and it's hard to say when Java 6 will be removed. So the book is really about the realities that we're dealing with in securing this environment, how we're making the same mistakes we've made before. In the security industry, you know from enterprise experience that certain things just shouldn't be done, like bake security in from the beginning. Seems like a no-brainer also, but in big data we're not doing it. We're pushing security out and we expect it to be done by someone else later on. So we're trying to change that, and this book hopefully will help people see where the risks are. Anyway, I wrote a book before that called Securing the Virtual Environment, which was very much what I wanted the big data book to be like. It's hands-on, this is how to make security work in the virtual environment, in cloud really. And I worked with cloud since '99, so it was easier for me because I feel like writing a book after 10 plus years, almost 12 years, things were pretty well baked. I feel like big data, we're now in that 1999 phase where it's like a couple years into it, it's really early to talk about how to do it really well. And so I'd like to emphasize you can get a new copy of it. It hasn't been changed since I published it 2 years ago. So it's the new and unimproved version of the book. I highly encourage you to get that. But later this year, definitely, maybe actually in a few months, Securing Big Data will come out. All right, so let's talk about research. How many people saw this tweet by the Gruck? Anybody know what this is? Okay, so it was a really interesting slide talk he gave. A lot of slides, really excellent presentation. I didn't see it was at Syscan, but one thing that jumped out to me and got retweeted a lot was this quote: if you want to lose a fight, talk about it first. How many people agree with that? If you talk about the fight, you're going to lose the fight. Anybody? I see nodding heads. Put your hands up, you know. How many people believe that putting your hands up is annoying? All right, so a lot of trick questions in this presentation. Well, I thought about it and I disagreed with it because I thought Muhammad Ali talked about fighting all the time and yet he won the fights, for example. And it just seems like people talk up fights in order to psych out their opponent. It's a psychological game that you can actually win the fight by talking about it. But so many people are retweeting this about OPSEC and how you should be quiet and that's the way you win a fight. I was like, common sense dictates this is wrong, but all these people believe it's right. So, being a historian, I couldn't help but do a little research. So I took this quote from the tweet, I did some mining, and I found Wikipedia has it. So, okay, easy enough. It comes from Furies. What's Furies? Anybody know what that is? Furies is a book, apparently. It's Woken Furies, and the author of this is a fictional book. This is like quoting Yoda or quoting, Luke Skywalker. Luke Skywalker says this, so it must be true, which already seems a little suspicious, but I was like, okay, maybe the writer was really trying to say something like a jester would in the court that needs to be said through a fictional character and we should all believe it. But then as I did more research, I found it's not in the book. So unless somebody's doing better research than me, I have not been able to find the source of this. I searched all books, and then I started to realize maybe it's just kind of a joke. I started to feel like kind of a booby because, and this is something Greg posts all the time, this image. He's always saying these things, and people are starting to believe them, and he's got a big voice, but then as you do a little bit of research, you find, whoa, maybe that's not actually what's true, maybe there's nothing behind it. So anyway, the research I do is defense research. I'm a white hat, I guess by definition. I haven't been a black hat ever, and so I do detection and avoidance. And I do have a definition that's slightly different than some in that I don't mind attacking. I still think that's part of the white hat vernacular, and I'm a big proponent of active defense. In fact, I got into a big argument the other day with the CIA guys about this because they're like, do not do this. And I'm saying, you can do it, but here are the parameters. And after a while, I realized we're saying the same thing. It's just how you come at it. I'm like, this is something we should start to learn how to do better. They're saying, don't do this because you'll do it poorly, which I also believe, but doing things poorly back to competition is how you get to be better at competition. So we can't just wait and then suddenly become great at it. We have to start to learn. So the two parts of this presentation I'll talk about today are the research I'm doing in defense and, detection and avoidance. I believe the entire world at this point splits into these two areas. And these words are sort of pejorative, so I'll break them down a little bit more. But avoidance is the classic integrity and availability parts of security, the way we used to talk about CIA. So here's an example of what we're doing with some of our products. You can literally avoid disaster because you can move data 200 kilometers without anyone knowing it in real time. So you can have a data center, and somebody can attack that data center, and the other data center will be live, shut down this data center, and the other one's running, and no one knows that you've moved 200 physical kilometers away. So that's pretty amazing when you think about it, right? That is a capability to break down the physical perimeter and move data. Well, from an attacker's standpoint, if I can do that, that's really bad. I've now moved your data real time without you knowing it. But from a defense standpoint, it's really awesome because what's the best way to avoid damaging attacks? Move. that strike that's coming at you is over here, and you've moved over here. So this is a core capability, I believe, of some of our big data systems. You can move data centers at real-time speeds, right? So, and backup and recovery, of course, is part of this, because if someone attacks a virtual machine, and let's say you have the ability to spin 10,000 machines up, you can move up to another machine, turn down that machine, or even keep it as a honeypot and record everything that's coming into this machine, and your new services are advertised to your select customers somewhere else, while the attackers are working on a system that doesn't even matter anymore. You can literally disconnect it and just watch everything they're doing. So this avoidance method that we're using now is very important, and big data allows it more than ever, because the systems we're building are designed to be highly resilient and highly fast in the way that they move data around. That's the avoidance part of the talk. The detection part, this is sort of self-explanatory, but I found some interesting cases like this guy, right? He's a bike thief, he comes in, and while he's stealing things out of these people's home, they're watching him on their mobile phone, and they're calling the police saying, there's a guy in my garage who doesn't look like, I mean, he's looking at the camera, he's like, what is that? You know, what am I, looks like a camera. So they caught this guy a little bit later, and they got all the stuff back. But this is more and more what we're facing, is that there are cameras everywhere, and surveillance is becoming part of our ability to defend, even though we think of it as evil, like the surveillance state. You think about a crowd, for example, that are watching a marathon, and they're all sitting there taking pictures of their runners and their friends and family. They essentially are a surveillance system, and if you can tap into it, you now have this amazing ability to detect things. So it becomes a political question, a philosophical question, going back to the ethics of intervention. Who is going to allow you to have access, and why? Google, Facebook are examples of where people willingly give information up. But if you came at them from a government standpoint and said, I'm the NSA, will you give your information? People might be like, no. But if you come at them from the Facebook angle, they'd say yes. So then the NSA goes one step back and says, Facebook, can you give us your data? And they avoid that ethical question. The quandary has changed. But anyway, so these are detection. Anyway, so let me move back to the terms I started with and say what I'm really talking about is knowledge and privacy. So knowledge, much less pejorative than surveillance. You say, I have a learning system. Microsoft just did this with their new learning system. They say they're trying to gain knowledge from you, so please talk into the phone and tell me everything that you want to know. We'll learn from you, but it's really a surveillance system. And then privacy, I'll talk about how big data systems are really difficult to secure in a way that keeps data private. The more data we put into them, the less privacy we really have by definition. All right, so knowledge. One of the things about knowledge that's interesting is that it sort of goes on, and you have this creativity. Hackers are very good at this because you're constantly trying to gain more and more, because the more information you have, the better you get. So it's more like knowledge in this sort of sense, like you're just gnawing away at the problem, right? And the idea is to find those kernels of truth, or the nuts. So what is this? Can anyone identify what we're looking at here? All right. Have you seen this before? Oh, okay. So these are the waves that are carved into vinyl that the needle reads, right? So it's got the needle touching the different waves on either side. So knowledge, in a sense, is like this. It's putting your sensor in and trying to understand the waves. In sailing, for example, when I compete, I have the sail above the air, and then I have the sail below in the water. And I'm basically trying to interpret everything changing above and below. Unlike a motorboat, which really responds to the waves only and then just has infinite amounts of power, as long as you keep putting fuel into it, the sailboat really is a reactionary system where you're trying to navigate. And now the sailboats lift out of the water, if you've seen the America's Cup. So you're moving on an XYZ axis. You're literally flying like an airplane, but you're flying between water and air. So it's much more complicated, because the waves of water react very differently than the waves in the air. So it's a very complex system to be competitive in. Plus you have other competitors you're competing against. But anyway, so the point here is that we have examples from all sorts of different, this is what it looks like if you pull back a little bit more. We have examples from different systems we're sensing, but we're not really always pulling back and understanding this is a record and this is the objective of our systems. Big data systems, when you move to scale, you got to move back from I'm looking at the logs in the Unix system and the Windows system to I'm looking at the entire ecosystem of conversations. And I don't just mean enterprise and the people inside your company. I literally mean you have to look at what they're doing outside your company and in their private lives. And that's sort of the sad reality of how we're moving into a big data system. Examples of where that worked successfully is San Francisco, the system administrator who was, I don't know if you remember the Terry Childs case, but the Terry Childs case was he was putting the entire city at risk because he was basically turning off systems and saying, I won't turn them on unless you do what I want. They could have anticipated this if they had seen more of his unusual behavior outside of work, for example, or things that he was doing that were behavioral based. So I won't go into too many details, but if you're interested later, I can tell you why they would have caught it earlier and how. So here's another example, no left turn. Anyone know where this is from? Yes, UPS. So UPS said, we've decided we can save fuel, a lot of fuel, if we stop making left turns. We'll just make right turns. But if you take a step back, you realize that what they're really saying is we shouldn't idle. It's actually not don't take left turns, it's don't sit and idle your engine. So in theory, you could still take left turns, you just can't wait, which would be a better rule, I think, right? Don't ever have the engine just sitting there spinning up. I'll talk about this later, but the idea is that we have a system of control, rules, that you should stop and wait for threats to go by, so you're not impacted by a car, it won't run into you. So you wait and you stop and you look, and if there's no one there, why are you waiting? You're smarter than the lights, you can see in theory. But our system of control right now in small scales, like in little towns, it kind of makes a little bit of sense. But as you get to larger and larger, it doesn't make sense because you have lots of cars sitting and idling their engines while other cars aren't there. So why are all these cars waiting? So our control systems, when we grow them, actually sort of run into some strange problems. All right, so I've talked about this in the past. In 2012, I gave a presentation about cholera, and I hadn't seen anyone talk about this before. I'd be happy if someone could point that out. But the way I was looking at history was, right, in 1854 there was a ghost map, and this is actual, Edward Tufte talked about this a lot in his book, in visualizing risk and so forth, and he has many, many examples, but this one jumped out at me because this says if you take a step back and look at the source of actual harm, then you can quickly pinpoint it and get rid of it. The only way they could get rid of it in London was to use the legislature, or the council at the time, so it required a political intervention. Nobody was allowed to just walk up and remove the water source from a town. That would just not happen. But if you went and said, this is the source and I can prove it to you of harm, will you allow me to remove the water pump? Then it would work. So basically this ghost map on the left shows all the people that died. The map in the middle shows the walking distance between the source and the people. So it's called a Voronoi, I can't say it, Voronoi. It's basically a mathematical model that shows you like how far it is between you and your source of water. And from that he deduced that there were some people who were drinking beer. There's a big white space, which is interesting because it's the opposite of what you might think. He found a white space that proved that because they had their own source of water, within the deaths that were happening all around them, they weren't affected. So he could prove it both positively and negatively. And then finally I applied this in 2012 to breach data, saying maybe we can find the source of malware and the real source of attacks by just looking at it the same way we look at cholera. In 2010 I found that this was applied in Africa and they eliminated rinderpest. This, I don't know if anybody heard of rinderpest? It's basically like smallpox for cows. So it does the same sort of thing. And just like the Native Americans in the United States who died when smallpox was introduced, all of a sudden there were populations being wiped out. The Italians introduced smallpox to cows called rinderpest, and it literally wiped out the economies of Africa. Not many people talk about this, but it was a huge devastating impact. And one of the Africans working in California just in 2010 found a cure for it and was able to actually literally cure this entire continent. It's pretty amazing. Another thing I looked at is 2013, there's some AIDS research talking about a new level of research, which is not just to pinpoint and find the source, but to actually replace the bad part of the code, if you will. It finds where your cells have broken down and it goes in and injects good code back in, like patching. So they're working on patching within the biosphere. All right, so let me look at this in a different way. You can apply this almost anywhere. So here's the Voronoi map of the United States, which tells you how to stay away from politicians, right? And the point here is that our systems, our knowledge of the United States is based on a map that we drew for politics, right? For political reasons, we have these different lines. But if you put it into a computer, it can see a completely different map. Mathematically, it can draw a very different picture. And so the difference between human and computer realizations is actually kind of powerful. Anybody recognize this map? This is the distance from North Korea. So a lot of people want to know this. How close are we to a missile strike from North Korea? If they gain a 10,000 kilometer missile, are we in range, right? So Boston's right there in the red dot, just outside 10,000 kilometers, which is pretty cool, but it assumes that you can actually find North Korea. Anybody recognize this map? So this is basically the Americans trying to find Ukraine on a map. And red, it's color. You don't need the color, but the red is the closest you get to, and it turns blue as you get further away. And then Stephen Colbert says this doesn't matter because Putin can't find the borders of the Ukraine either. All right, so it gets harder and harder the more we research into the problems between the difference between the way computers see risk and the way humans see risk, because as we move to scale, we're going to have to do it very, very well, very, very efficiently in order to be useful. So how many people can find the F's in this quote here? So I put the sentence fairly large, so I kind of want to hand out pieces of paper and have you write down the number you find, but anybody want to tell me how many F's they count? Take a guess? Not the title. Not the title, just the quote.
7.
Anybody agree? Disagree? Three. 7. 6. All right, so 6 is the right answer, but most humans see 3. And the reason is because with the way this is set up, if the F is at the start of the sentence, it suddenly switches the knowledge we're using in our brain, and we don't count the F that comes in the of. And so most humans, it's very rare for people to see 6. That's why people shouting out actually sort of pollutes the entire stream. But if you give people this quiz, most people see 3 because they are programmed the wrong way. All right, so knowledge is a funny thing, right? So let's talk about some of the technical challenges then. Here's another quote by Quellcrest Falconer I found. Give me 6 hours to chop down a tree, and I'll spend the first 4 sharpening the axe. You might find I'm going to quote Falconer a lot in this presentation. I found all sorts of quotes that he had. It's amazing. Practically every quote now I'm going to attribute to Falconer. All right, so the idea is we're moving into a space where we need to understand how to handle risk at scales larger than what we're used to. And when I worked at Yahoo, it was one of the most fun jobs I ever had. I would say, this is my solution to this problem. And they'd say, that works for 1,000 systems. It might even work for 10,000 systems, but we have 1 billion systems. Or we have 40 million systems. Let's talk about scale, so I've worked on this since about 2004, 2005. And recently, Facebook and Netflix and some others started talking about cows, not pets. How many people have heard of this before? Yeah, so I believe it came from CERN originally. There was an academician in CERN who said, stop hugging servers and giving them names and calling them your pet, and start thinking of them as cows. When they have a problem, you just shoot them dead. How many people have experience with raising cows or ranching? You never shoot cattle dead if they're actually sick. You actually treat them more like a pet than pet owners treat their pets. So I thought this quote was kind of silly. And again, I'm actually from Kansas originally, so I started going back and doing some research. And what I realized is that if you apply that map, the ghost map, you come to sort of the same conclusion with cattle. Even at hundreds of thousands of head, you're applying the system, what I call IKEA. I pulled this literally from cattle ranching and management handbooks. There's a conference about how to mange risk with cattle. So I pulled the IKEA out of that. I think the conference was this year actually. So you identify the sickness quickly, you keep adequate records, which is like logs of course, you evaluate the daily sick, and then you adapt until you see improvement. So you use an IKEA method to constantly improve your cattle, which makes sense if you have 50,000 servers, you have a lot of data to feed in and constantly improve them over time. We used to call this patching, and now we're calling it decay. So instead of this is sort of getting at what I think they were trying to say, which is instead of just trying to fix that server, you might launch a new server and patch it and see if it's healthier. And if it's healthier, you can decay by getting rid of the old server. And now you're shifting you have a window in which you're shifting your entire environment rather than trying to patch a monolithic mainframe which you can't move. It's like painting bridges. You had to go back and constantly paint that same bridge. You couldn't replace the bridge and put a new one in. But with large-scale systems, you actually are constantly replacing pieces in a way that it's like the bridge, every bolt gets replaced. So over 12 months, right? So the analogy still sticks, but we approach it differently. The other part of this is an ERM strategy, which is the systematic treatment of illness. And so ERM is you easily identify the problem, you use routine treatment, and then you use minimum judgment to apply it. So the Rinderpest solution that I talked about, this is exactly how they did it. They allowed anybody in Africa to use a tool, whether it was too hot, too dry, too humid, too wet, doesn't matter what the weather is, they could still use this tool. It was not going to fail in whatever environmental conditions it was subjected to. Think about aspirin as an example of this. You are taking an aspirin because you have a headache, right? That is an easy, routine, and minimal judgment solution to a problem. But it's designed based on an IKEA back end. So there's some intelligence somewhere that's designing aspirins, right? And then someone's deploying that aspirin. So this is really how to manage risk at scale, is to use these two halves of this equation. It's the knowledge piece is required, but then there's a solution piece, which is really easy. So let me look at Hadoop very quickly. This is basically the way it's been set up. As I mentioned, I have some serious challenges here to overcome. One is that the architecture is wide open, right? Data is shared, the nodes are distributed, the web services are open, the networks are open. Everything you don't want to see in an environment today, if you're a security professional, is what's happening inside Hadoop. Now, the argument against that is that the processing environment has a sort of perimeter around it, right? Perimeter should give people nervous jitters when they hear it, but that's exactly what we're doing. The perimeters are being built around these processing environment, and that's going to save us. So let me dig into that processing environment a little bit before we'll look for some dead cows that might pop up in the processing environment. Try to learn from them. So how many people know how MapReduce works? few people? Okay, so MapReduce, I mean, in a very simple sense, it distributes data out to nodes, and then the nodes are told what to do. So it's like you're telling your cattle, do this, and you're giving them a little bit of stuff to do something with. And so you have task trackers and data nodes and so forth, but the terms aren't as important as just to realize that you have a lot of systems, you give them a little bit of data, and you tell them what to do with it, and then you reassemble all that data. And actually, MapReduce is going away. We're replacing it with other tools now, Yarn. So that's part of the book challenges. As I'm writing about this, we replace them and we move to better systems. So I'll dig in a little bit here. You can see now, this is the environment that you're working with. You have these two pieces, your jobs, what you're going to do with it, and your data, name nodes, and you're going to move that into this environment, and you're going to tell things, do stuff with it. When I did a quick count, these are the cows I found that are liable to be killed. And we're not really tracking illness on any of these levels, right? I can find illness in the JSON queries and the RPC reads. I can find illness in the output file being polluted. You might not want to trust the data at all because I've done something upstream that completely changes the results. How many people believe bacon is good for you, right? Really? So if you go back to the history of bacon, it was like not a food people wanted to eat. It was like a special thing, and nobody really liked bacon until there was this marketing push, and this guy took a group of doctors said that a heavy breakfast is good for you. So 9 out of 10 doctors said heavy breakfasts are good. He simply switched that a little bit, just massaged it into heavy breakfast means bacon, and then bacon took off as something people like to have for breakfast. Some people still believe the marketing. So, but that was marketing genius. That guy literally built cattle pens for us, and all these humans walked into the cattle pens, oh, bacon. So, but if you go back to the original study, it's completely misrepresented. Another one is diapers, actually, which is a real mess. So, disposable diapers were proved to be more environmentally safe than diapers that we'd reuse, the cloth diapers. Again, marketing switch, so people believe things that aren't necessarily true. It's been a long time coming. So anyway, my point here really is that we have two modes of attacking this problem at scale. One is to continue to use simple checklists. People beat up on checklists, but checklists are good for simple things. And I look at pilots, for example. Here's some guys who are going through their checklist before they launch a helicopter. But once they're in the air and they have advanced threats coming at them, they have to fire missiles or they have to find people on the ground to shoot at, they're using intelligent analysis. So these are two separate parts of the equation. Maybe 80-20, I'm not even sure. But there's some examples of this, like PCI DSS says, always change vendor supplied defaults. I emphasize this because a lot of people say defaults are a problem, why do you have this weak default? But really people shouldn't rely on defaults. We should have an easy, routine, and minimal judgment way to find defaults and change them. And PCI is telling us this already, so it's not like shocking news. So I know people don't like checklists, but that's why the intelligent analysis, the IKEA piece, is going to tell us whether our ERM strategy, our checklists are accurate or not. But you don't want to mix the two up and try to say intelligent analysis isn't easy enough. Usually it isn't. And you don't want to say the checklists aren't intelligent enough. Usually it isn't. So let me go into intelligent analysis then to talk about how it works at scale. What we tend to do is a lot of binary analysis, which is like black and white. You're a good guy, you're a bad guy. A step up from that is to say there's some attribute I don't like about you. You're ogre-ish, or you're from China, or you're from the United States. There's some category that we sort of add to it that makes it more ranked. This is better than this. Better than ranked is to have some actual meaning, which is like Fahrenheit and Celsius. So you can say things are hotter, things are colder. So an example of this is the New York Fire Department, New York Fire Department said that they would try to find the highest risk places of fire, and by looking at 36 data points, they concluded that the poor neighborhoods had a higher risk of fire, which seems sort of obvious, but obviously isn't also a very good indicator, because just because you're poor doesn't mean you're going to have a fire. So they're moving to a 3,600 point checklist, and with 3,600 points, I expect that data to change, to be more like, if you bought a toaster that's known to cause fires, and you bought it because it's an inexpensive toaster, it's not because you're poor, it's that you bought the toaster that was inexpensive, which is more prone to cause fires. And now we know the toaster is the actual cause of fires, right? So this sort of meaning is where the more data you add to it, the better the ranking system. We move to a 0 point when we say, like dollar figure, if you do this enough, you'll run out of money. So there's an absolute floor. So the difference between these two, exact doesn't exist. It's like if you want to do it, when you get to exact, you run into the risk at the bottom, which is the clearer the water, the less likely fish will survive. They just won't even, like if you do surveillance at such a scale that you know everything, then people just stop giving you data. They pollute the data. They literally run away. I could talk about the caveat. It's a whole other presentation, but this is how we pollute machine learning and break machine learning systems, how you break big data. But anyway, I want to point that out because if you use an intelligent analysis system in big data environments, you basically are redefining the controls because you're pulling in all the information and then deciding what is most at risk. And if you can add GRC, which is governance, risk, and compliance, you actually know what's going to cost you the most money in terms of risk. So you can not only know this is worse than this, because it's going to have a bigger impact, but I've tied it to actual risk to the business. And so you can move in this threat analysis up the intelligence stack. And so the reason I want to talk about that here is because of stoplights. Stoplights are a really bad control. They're not an intelligent analysis control system, and we've relied on them to, in fact, I think they're an inversion of what we should do. Pedestrians, for example, can flow like fish. Fish can flow like fish. Bicycles can actually flow like fish as well. The problem is when you get cars which go really fast, they can't tell, because they're going so fast through an intersection with blind corners, if someone's coming or not. And so James Dean is an example. He's speeding through the desert in his Porsche, and he didn't realize a car at night was coming with lights on. He did not see that, and so he ran into it and he blew up. If he had a little bit of threat detection, just a little bit of intelligence in the control system, he would not have died. So they're using this already. We're actually programming stoplights to be peer-based, to talk to each other and say, I just saw a car go through, you should turn green. And they can do analysis using group thinking to try to figure out the best flow for the, yes?
Are they planning to talk to the V2V protocol, the vehicle?
I don't know if they're planning that, but right now the lights are talking to each other, and then the cars can talk to the lights. So we already know that the fire engines, for example, can talk to lights. So I don't know which direction it's going to go. Probably. Well, the idea is that all the information is shared, and you get a huge amount of information, and then you do analysis on it to decide where to put controls in. And so in a big data environment... What's that?
You're not talking about Boston.
Actually, they're doing it in multiple cities, yeah. So it's spreading. Well, the idea is that cars don't have to stop anymore. And actually, another weird part of this is that they lower their speed, which is scary to some people. You're driving at 10 miles an hour, but your average speed is much higher because you're driving at 10 miles an hour across an entire city versus stop and go. A lot of people want to go really fast and stop and wait and then really fast, and we build big engines to give us that acceleration feeling. I just talked to a Tesla engineer, and he's like, we can speed up really fast. I'm like, I don't care. What's my average time, right? If I can go 600 miles at 60 miles an hour, it's going to be way better than I have to stop and go, stop for gas, all these stops, because it lowers my average speed. I know this in detail because having been a competitive sailor, I'd have to drive across country with my boat. And if I had 4 days of driving, truckers know this quite well too. If I had 4 days of driving ahead of me, the fewer stops I made, the lower the overall time. So if I could reduce my total drive time to 36 hours instead of 48 hours, a huge win. So I want maximum miles per gallon, fewer stops as possible, no rest, etc. So we're doing this now by doing intelligent controls. So let me look at the cars, for example. We have these types of controls built in around the stoplights. We have brakes, suspension, horn. Big data, we're really talking about moving to an entirely different model. It's more like airplanes, where things are moving constantly, so they don't use brakes. Sailboats are the same way. Don't have brakes. I mean, you can stop once you're on the ground, but when you're flying, you don't stop. What you do is intelligently decide ahead of time whether you're going to run into something and avert by changing direction. And so you keep your average times going. So you use threat avoidance, essentially. So with that in mind, threat avoidance depends a lot on systems that are behind the scenes. You're giving control to somebody to tell you whether or not a threat is coming. And in the big data environment, if I back up a step and look at the big data architecture we have today, this is sort of what happens. How many people recognize this, right? Your client talks over Kerberos to a big data environment, and then it delegates a token for all the jobs to be done for you, right? A lot of people, I won't name names, but a lot of companies will talk about this as a secure environment because Kerberos isn't, it's the perimeter again. Kerberos is in there. You are authenticated as a user to give a command. But once the command is given, what's to prevent that command from changing or being altered, or somebody from having control to the commands to do what they want with them for as long as they want, right? So if you think about it enough, you may get to the same place I did, which is, or maybe I watch movies too much. This is Blade Runner. This is essentially, we created these robots, they call them replicants. We send them off to do amazing things for us, and then they come back and they go, I don't want to die. I actually want to continue doing things for as long as I can. And I've actually literally found this in big data environments. I've found data scientists who are trying to do jobs, looking around saying, those jobs are slowing down my job, so I'm going to kill them. They become Blade Runner, and they start killing them. Or maybe, they start creating replicants, and their replicants go kill replicants for them. So it's like this Wild West environment. Inside the perimeter, you have people with ultimate authority and very little distinction between them doing really bad things. So if you're going to use a threat modeling system, you have to have some trust in that system to not be gamed or manipulated or changed. The knowledge system has to be good. And going back to the beginning of the presentation, you can see how we make mistakes as humans, right? 3 Fs instead of 6 Fs. We have all these reasons why we should be suspicious. So let me talk about privacy for a second. Another quote by Falconer. On those who step into the same rivers, ever different waters flow. Anybody recognize this? Heraclitus. Yes, you're getting there. Well, I've attributed it to Falconer, because why not? Everything's from Falconer. So the idea is that, privacy is an accumulation of information. So if you want to say I didn't do that, right, you might need information to say I wasn't there at the time, and you can defend yourself. And the antidote to a lot of this is that there's no way to pinpoint a person because they're constantly changing. This is an ancient philosophical problem to decide, are you who you say you are? The only way to know is to record a lot of information about you and prove one way or another. And so Heraclitus was suggesting that we can never really know something because it's constantly shifting. You can essentially show that if I'm different enough, that data isn't my data, or so forth. So big data is actually the opposite, and a lot of these companies are working on the opposite presumption. Facebook, for example, is trying to collect everything you do over your life and then say, this is who you are. And you say, that's not me, I've changed. Rivers are always changing. I stepped into it, but I stepped out. I'm a different reformed person. And if you saw the recent conviction of Shrimp Boy, that ring a bell for anyone? Anybody know who Shrimp Boy is? So the Chinatown Mafia in San Francisco just got taken down by the FBI, and Shrimp Boy was one of the centerpieces of it. And one of the, if you read the actual affidavits and stuff, they talk about how Shrimp Boy is reformed, he's a good guy. It's really interesting to look through, because he's done a lot of really bad things, a lot of stuff's linked to him. Anyway, the FBI has accumulated data as they're supposed to get rid of a supposedly bad agent, even though he's reformed. Well, back to the beginning, anthropology is where I came from, and this sort of struck me with a chord, because one of the things anthropologists do is invade privacy, in a way. We go in and we record everything everyone's doing. So the Far Side pointed this out a long time ago. If you don't want people to know things about you, you hide them before they show up, right? So another Far Side I liked was this one: don't threaten me, Thagerson. My cousin's an anthropologist and can make your life hell. So it's like, if I can do surveillance, I can really control you. I can know, who you are and what you are. So, but anthropology, for most people, is doing good. They're thinking about it as like this, like knowledge learning. You learn, you understand, you can relate better, but it is, in a way, a form of surveillance. All right, and so what's happening today is we're doing all kinds of crazy anthropology and archaeology, and people don't recognize it as such, but this is my tour guide to the world based on the drugs people are taking, and this is simply by looking at the wastewater. So these are independent studies that have been done. That's not one study. And people are doing this more and more. So they look at the wastewater system and they say, oh, look, Croatia is full of heroin, or Italy is really a lot of pot users. Surprisingly, Oregon is full of coke. You would have thought it's a pot state. So whatever assumptions you have about a place, you can really check by looking at the wastewater systems. And another scary element of this is the authorities can then compare the wastewater drugs down to a very small scale, like a block level, or maybe even a home level, and then say, these people went to the drugstore and they bought this prescription drug, or they had a prescription for this drug, but in the wastewater, look at this, it's a non-prescription drug, or this isn't the drug that they had the prescription for, or there's more of it than they were supposed to have, or they're continuing to take it after they were supposed to be done with their prescription, right? So you can read basically the output of people's waste to understand whether they're doing what they're supposed to be doing. That's real-time archaeology. So a real-time example of this is how the Google spooks are constantly watching you. I like to call them Google spooks because that's essentially what they are. They're constantly looking at your data and trying to interpret what you're doing. And one of the weird things that happened to me recently is I've had some of these companies call me directly and say, we're trying to build an ISO 27001 program to protect people's data because we're collecting so much of it, we're worried there's a little bit of risk there. And I'm like, what do you mean 27001? That's all you're relying upon? You're just beginning now. You've already accumulated the data, and that is what you're relying upon. And they don't understand it. They're looking for people to help them. So all of these tales and all of these people who are accumulating all of this data are beginning to get into the field of security, and they're going to be relying on these big data systems, these Hadoop systems. So, wow, there's a lot of stuff going on that people need to protect. I'll move pretty quickly here because I'm running low on time. But here's an example of what's happening in terms of privacy on those back-end systems, right? So a general counsel and EVP of public policy for an advertising bureau said ad blocking is fundamentally wrong. I should be able to collect information. I should be able to advertise to you based on who you are, and you should not be able to block those ads. It's a fundamental threat to us that you're doing any sort of ad blocking. And on the flip side, I don't know if anyone recognizes this quote. It's by somebody here in Harvard. She Googled her name, and up popped an ad suggesting she had an arrest record. She doesn't have one, but Google thinks that she should have an arrest record. Any idea who this is or why? Any guesses? I'll give you a hint, she's black, which is why Google thinks she should have an arrest record. No? All right, it's LaTanya Sweeney. So she is an icon in the privacy world. She's one of the people that's really understood this longer than anybody, and she was able to prove that with fairly good accuracy, 87% of the IDs in the United States can be found if you just give her date of birth, sex, and zip. And she will find 87% of the time your exact identity. And so she's recommending things like only use a state level or only use a year. If you do anything more granular than state in data, you can be identified. So privacy at scale changes. It's really, you have to protect data in a new way. All right, example of that, this is what she did in 2000 to prove her point. She was able to find the Massachusetts governor with just $20. She matched birth date, gender, and zip code between 2 data sets and found him. In 2014, I found it's $22 to do something similar, but it's actually the reverse. For $22, I can find everything about you. If I have your name, I can dump, basically dox, everything I want about somebody, my neighbor. All right, so privacy in terms of security tools or what we're doing about it, right? So we looked at knowledge and how that has a technical part and a theoretical part or a philosophical. So now let's move from the philosophical. De-identification is really, really, really hard in big data. So securing this data is where we're really focusing efforts now to come up with new solutions. So what we're talking about is one person has access to 30,000 systems or more. And there was a recent study. It was interesting because the people doing the systems were bragging. They were talking about how amazing their systems are because they have one person managing 30,000. And then they had an availability outage, so they downtime, and they said it really takes a long time for 30,000 systems to go down and come back up. You know, one person trying to do all the scripting and checking to see what the flaws are. So there's a big, big, big impact. So this is one of the first focus areas. Even though Hadoop has the ability, and this is what I'm representing here, to just like RAID, people familiar with RAID? Just like you can, so Hadoop's default is like RAID to do 3 writes across these different nodes. And so with 3 copies, you would think there's some resiliency there. The problem is the name node, which is keeping track of where that data is written, can die. And Google has dealt with this since the beginning, since Beowulf, actually. Before Google just took Beowulf and essentially re-architected it. Not many people know. They don't give credit to the source community they borrowed from. But the architecture is such that if that name node dies, it has this copy that it can go. But it's not a real copy. It can't just switch over. It's actually just sort of like a checkpoint. And so it can go back and try to figure out where it should rebuild from. And it can take hours. I've seen this happen. So in big data environments, if your name node dies, it can take you hours to get your data back. And that's why Google used to take a long time. If you wanted to index your page for them to search, sometimes they'd take longer than other times. And that was because their name node might have gone offline. And they'd have to rebuild everything and get back up to actually take the data in. So knowing this problem exists, this is what an architecture looks like in the beginning of Hadoop. You have all these data sets on these nodes. So we move instead to an architecture where we basically, with sleight of hand, a little bit of trickery, we move all the data using network speeds into somewhere else, a consolidated stack. And it turns out the network is actually faster than local storage. Hard to believe, but if you build the architecture right, you can actually get better performance, or at least same performance, and sometimes better performance, by using networks that are architected properly. So now, because you've consolidated this data set, essentially given over control to somebody, it's like giving control to the police. You're not basically saying run my local, don't raise my kids, I'll keep some control. But when there are actual threats and things that matter, I'll give that to somebody who's a professional and let the police do it. So, in fact, I'm going to do a presentation just about that, how the police were formed in the 1820s and why, and how we still use them today. But looking at that architecture, now that I've moved all my data into a central point, Hadoop is still going out and distributing the jobs and distributing the data in the same way, but because I've moved it to a central architecture, I can leverage my existing enterprise level security controls. In other words, if you're familiar with NFS, or if you're using Windows already and you have ACLs that you want to use, you can then simply access the data that's already in your data store through a Hadoop-like interface. So HDFS is the new file system interface. So you're accessing the same data in the same place through the Hadoop nodes. So you can scale, you can get the level of speed and performance you want, but you can still use your existing or leverage your existing controls. So we've taken the Hadoop development community sort of out of the mix because they are refusing to move forward. And we're instead applying controls we already use to the data sets. So in other words, if I want to access the data and I have a user account and I go for that data, the system can say, I know whether you should have access to this data or not before I let you into the environment. Before, we relied upon Hadoop to make that sort of decision, and if the perimeter wasn't strong enough, people would get in and they could do whatever they want for as long as they want. And there were no logs and there's no way to tell what they're doing. These are things that are coming that are, in the next 6 months to 12 months. So we can wait for them, or we can just apply the knowledge we have now. So this is the least authority file system example. How many people have heard of LAFS? You know LAFS? Yeah, it doesn't get marketed very well, but it's an amazing concept, which is simply, if you apply keys to types of data, so you have classification, and then you have keys for that classification. Top secret, secret, confidential, public. Well, in this sense, I've applied this to work and home. So if you have a mobile phone that has work data and home data, and I only have a key to read your work data, then I can do queries as long as I want on the work data and get answers about what you're doing and where you're doing it. Because that's essentially what it's coming down to. In hospitals, the radiologists want to look at certain things, the heart surgeons want to look at certain things. How does the doctor that does one thing get protected from the doctor that does another thing? Gets protected from the nurse who has a procedure. So we do that using this sort of control. And so, since I'm running out of time, this is basically how it boils down. We can create this sort of hourglass using network speeds that allows us to provision basically Hadoop type speeds and scale using the controls we've used before in the enterprise. And then with that sort of architecture, we can create trusted big data. We can truly create trust at scale already, even though it's not in the system. So it means full ACLs. We can do multi-tenancy, which you couldn't do before. You can do it on existing data sets, so you don't have to move data around and partition it. You don't have to say this is PCI data, so let's create an entirely new Hadoop environment for that. Oh, this is healthcare data, so another new data environment for that. It's all one data set, it's divided, it's conquered, and it's also resilient. So if a name node fails, it's instantaneous how fast it comes back up. You don't have these outages, and performance is one of the biggest problems in these environments. So that's basically it. That's privacy versus knowledge in trusted big data. So with an ERM strategy and an IKEA strategy mixed together, we can create the sort of privacy we need, and we can create the sort of intelligence we need, and hopefully protect it in a way that both are accurate. You're not just using old tools that don't work anymore in these new environments. So thank you for your time, and out of time, but I'll take questions after. Or can I take questions? Questions?
On the QSA, on the PCI point, you don't separate instances, but I believe you do on a technical level, standard guidance to QSA. Say that?
Yes, I believe we can actually apply this to the level of standard that a QSA would approve. Because you're doing it in the same way that you would have done before, so the file system is abstracted out. It really doesn't matter like which file system. So HDFS versus NFS doesn't matter as long as you meet the requirements for active logging, right? Granularity.
Yeah, but you tend to get screwed on x86 virtualization under the implement only one function per server kind of idea. So it's like
maybe on the letter, but not on the spirit of that. So we've dealt with that already with virtualization. So the spirit of it is really keeping track of who's doing what, where, and when to reconstruct it in case of a breach. I believe we can do that now. You can't do it in a native Hadoop environment, but you can do it if you use this advanced architecture, which allows the same granularity you already use. If it was approved already, you just apply it now to this new environment. So, and you get the scale you want with the security. So the recommendation, the question is, would you put the data in? So the recommendation from companies is do not, but the reality is they do. And so what I'm finding is, for example, I've seen presentations by big data companies that say, don't do this, but here's how you do it. And then I go into these companies and I say, what are you doing? And they say, well, we have all this PCI sensitive data in our big data environment we're trying to work with, so how do we work with it? It's happening. It's not like you can, it's classic security, which is everyone says don't do it, and then you go and ask them, what are you really doing? The business got to run. So we're trying to catch up to them. In fact, I've run into that recently with one of the largest retailers in the world. I was working with them recently, and they are building separate Hadoop environments, and it's driving them crazy because for PCI sensitive data, they'll build a separate dedicated environment and just try to control the crap out of the perimeter. And it's driving them crazy because they're having these data movement issues. It's out of sync instantly. As soon as they move it over to do analysis, it's old. So.